All right, I think 10 minutes have passed. I didn't check when we stopped, but let's get going again. So welcome back. So this lecture is going to kind of morph directly out of the last one. So in the last lecture, which was only a couple of minutes ago, so I shouldn't have to recap, but I will anyway. What we saw that the Michelson interferometer alone cannot do the job that was needed to detect gravitational waves. It needed these enhancements, which were done by optical cavities, also known as Fabry-Perot cavities. Now, what I'm going to do is we've now set ourselves up for what the optical parts of the interferometer should look like. And so now I'm going to go ahead and talk a little bit more about the fundamental noise sources that occur in the detector and how we get around those. So I'll just remind everybody of something that Scott also reminded us of yesterday. So the gravitational wave measurement is as simple, if you wanted to think of it in the simplest terms, as simple as me shining a laser at a mirror. This is a good mirror, it reflects the light right back to me. If I had a good clock, I just measure the light travel time, measurement done. Okay, that's the principle of the measurement. Now it turns out if you plug in the numbers, even for these kilometer scale detectors, we don't have good enough clocks by orders of magnitude. And as a result, the interferometer becomes useful not just because it's perfect for this quadrupolar term that gives you twice the signal, but it's really important because what the interferometer really does is one arm of the interferometer acts like a reference for the other arm. So you no longer need a clock with absolute precision. You're making a relative measurement, okay? And this becomes even more interesting in the context of the fact that we operate at the dark fringe, because it's a device which is operating around a zero, which is a very powerful technique in experimental physics. Okay, so we're going to make the mirrors very still. I'm going to talk about that now, and then we're going to probe the mirror positions using light, and I'm going to talk about that tomorrow. Okay. So a quick tour of what these detectors look like. So this is an overhead view of the LIGO Livingston Observatory in Louisiana, and you can tell it's Livingston because it has a forest around it. This is what the beam tubes look like. So the laser beams run inside of these stainless steel tubes, which are under ultra high vacuum. So the vacuum inside these tubes is something like 10 to the minus 8 torr of hydrogen, which for people who work with vacuums in the laboratory is quite doable. For people who want to evacuate 20,000 cubic liters, that's a pretty big deal. Okay, this is the housing, a concrete housing that goes over these beam tubes, and that housing has proven useful at times. This is a patrol car. This is now at the Washington Observatory. You can tell it's not a forest, it's a desert. And this patrol car came flying over this dune and didn't notice that there was this 4-kilometer long barrier in the middle of the desert. Okay, luckily no one was hurt, including the instrument. Okay. If you go inside of the main hall, you see objects like this. This is every one of these is a vacuum chamber connected to each other by these vacuum tubes. The size of this is, to put a scale on it, when I stand beside one of these vacuum chambers, the top of my head is just below this row of viewports right here. So these are pretty big objects. Is there any reason that the tubes are not underground? Yes, very good reason. It's expensive. Yeah. So, and I'll say a little bit more about that when I talk about third generation detectors tomorrow, which is when you're thinking about detectors that are no longer 4 kilometers long, but 10 or 40 kilometers long, you no longer have the option of not tunneling, because now the curvature of the Earth makes it impossible for you. So 4 kilometers, it turns out why 4 kilometers? It's kind of the longest you can go without needing to tunnel when taking into account the curvature of the Earth. Okay? So here are these chambers. Each one of these chambers holds one mirror of the interferometer. Now I've shown you already that this interferometer has quite a few mirrors, right? There's not just the beam splitter and the two end mirrors, but there's all the Fabry-Perot cavity mirrors in between, and each one of them is in one of these. why do you need such a big house for a mirror? It's a house that's about the height of this room. You need a big house like that because you need vibration isolation. And I'm going to tell you about how we do that. But here is one type of vibration isolation system, which is a spring mass system that's stacked spring mass, spring mass, spring mass stack. The mirrors themselves look like this. They're about 40 kilograms in mass and about 35 centimeters in diameter. And this whole structure here is because the mirrors themselves are hanging like pendulums. And they're hanging like pendulums because, as Scott alluded to this a little bit yesterday, I'll go into more details. Above the resonant frequency of the pendulum, you get your free falling test mass. Okay, and I'll show you how we do that. This is the, I'll say here is the a close-up of a mirror, and this is, even though it might look just like nothing to you, this is probably the flattest piece of glass you've ever seen a picture of, okay? And then this is the laser, and this is the control room from where it all gets controlled. And you can see many, many figures of merit in the control room, including these pictures of the noise spectra. So this is what LIGO has looked like in this past, present, and future. So on the horizontal axis, we have frequency. You're used to seeing power spectra, and I'm going to go a little bit more into detail with these actually amplitude spectral densities. And here is the strain noise in units of per bandwidth. The green curve was what was achieved for initial LIGO, which ran from 2000 to 2011. And then from 2011 to 2010, 2011 to 2015, the LIGO instruments were shut down for a major upgrade that was called Advanced LIGO. And in middle of 2015, in September 2015, when the first detections were made, the two instruments of LIGO had sensitivity that's given by these red curves here. That's observing run 1. The ultimate design of Advanced LIGO is this blue curve here, and then the upgrades we're planning are the cyan curve. And I'll talk about the upgrades tomorrow. That's part of the future looking stuff. So that's what this looks like. So what I want to do now is to talk a little bit about how we go from the green curve to the red curve to the blue curve to the cyan curve, because that really is the process of eliminating fundamental noise sources. Okay? Now, I want to say one other thing. This is Ray Weiss, and Ray Weiss was one of the Nobel laureates whose pioneering work, and he's actually worked in this field ever since, was that in 1968 to 1972, but in 1972 it was written down, he actually did the complete set of calculations for what this green curve should look like. So in 1972, he had already written down and calculated out what all the fundamental noise sources would be, what are the things we'd have to worry about, what are the technologies we'd have to develop. And then the most remarkable thing is it's an unpublished paper. So all of LIGO is based on an unpublished paper of Weiss's. But the thing that I always find stunning is that when we achieve this curve in sort of the 2010 time frame, that was 40 years in the making. Okay? And then since then, of course, we've done better. Okay, so since we're going to spend a lot of time looking at these power spectra or amplitude spectral densities, let me just spend a couple of minutes bringing everyone up to speed on the technology and the naming conventions, etc. So what do signals in the time and frequency domain look like? So one of the things that we're interested in, particularly when we're characterizing noise, is random functions of time. Okay, so a typical time series can be the output of any measurement is usually a time series, and it can be either a deterministic function of time, like say the gravitational wave strain. It can be a random function of time, which is just the noise from the instrument when no signal is present, and of course it can also be both, and at different operations are useful at different times. So that's what we have when we have a time series x of t. we can take the Fourier transform of that time series, and the most important thing for us as experimentalists, and for the rest of my time here, I'm going to assume you're all experimentalists and are going to see this all from the lens of experiments. The important thing about this Fourier transform is it basically tells us the amount of sine and cosines at each frequency f that build up this time series x of t. And it's generally very useful to be able to go between the time and the frequency domain. And you will see in a little while when I come to control systems and linear systems that working in the frequency domain is particularly powerful, because in the frequency domain you don't have to do a convolution of time series. You can simply multiply things out, and so the algebra becomes much easier, which is very good for experimentalists who don't like math as much as theorists might. Okay, now then there is the cross-correlation function. The cross-correlation is essentially when you have two time series, x1 and x2. The cross-correlation is given by this operation here, which is that you time shift one of the time series by some time tau, and this basically then gives you a measure of the extent to which the shape of one of the time series matches the shape of another time series, okay? And it's often used in situations where one time series is deterministic, where it has, say, a signal, and the other is a signal template, and the other is random, like signal buried in noise. And here's a nice graphical representation of that. The top curve is a time series 1, and it has some noise, and within that noise there's some signal, and this is a very overt one. You can even by your eye guess maybe, just maybe this is some signal. This second time series is the deterministic one, and shown at different time slides tau, so at different time offsets, and when you hit the time offset where this time series matches this one, you get a large amplitude in your cross-correlation function. And that's what it's used for. So these cross-correlations are very useful for that kind of operation. Then comes the autocorrelation function. The autocorrelation function is really just the cross-correlation of a time series, but with itself. And the question that this is asking is that, it is a measure of the time scale over which a given time series both varies in time, but also repeats in time. So when you have something that repeats, that's often picked up by the autocorrelation function. And now the power spectrum, the thing that we always show. I'll show you. We often show amplitude density, not power, but that's fine. When you take the Fourier transform of the autocorrelation function and you normalize with the right units, you basically are forming the power spectrum. Now you notice that this integration is done over the time offset tau and not over the actual time t, because in this particular case there's some assumption that the time series are stationary, and so they have shared properties at time t. Now an important property of the power spectrum that we must recognize is it's just like a Fourier transform in that it measures what are the sinusoids at any frequency f that make up this time series. But it throws away all the phase information. And that's okay and pretty useful when you have random time series, because when you have a random signal, the phase doesn't matter anyway. It's a random signal. So that's an important thing to remember. You lose phase information. Okay, now experimentalists usually like to think in terms of positive frequencies, whereas this expression here can take both negative and positive frequencies. So we usually define a single-sided power spectrum, which is just twice the two-sided power spectrum for frequencies greater than 0, and otherwise 0 at all other negative frequencies. And we will use this version of the power spectrum. Now, there is another object called the periodogram. And the periodogram is essentially the Fourier transform divided by some segment of time t. And this is the version that Scott showed in his talk yesterday. And it's important for experimentally, because power spectra, if you say I measure a time series x of t, how do I actually make a power spectrum out of it? I essentially use the periodogram. So I don't have an infinite amount of time. I have a finite segment of time t. And so I take x of t in this finite segment of time, and I calculate the power spectrum from the periodogram. Okay, now the power spectrum is a measure of the extent to which this noisy time series contains components at different frequencies. Now, in a lab, this is an extremely important feature, because when I look at a time series, I may be dominated by some unimportant low frequency signal, and I'll miss something that's more important at higher frequencies that even filtering could get to you, but basically a Fourier transform is nothing but a series of filters. And so that's the other thing I want to add. The way that you could actually measure a power spectrum is you could take your time series x of t and you could pass it through a bank of filters. And basically you could slice it up into, if you were really crazy, you would slice up into 1 Hertz band pass filters, and it would tell you in each of those filter outputs how much energy there is. How much power that is. That's the name. So it's a very important experimental tool. And now when you want to go back from the power spectrum to measurements of, say, the mean value of some quantity, then you just simply integrate the power spectrum, and I'll show you that next. Okay, the amplitude spectral density is simply the square root of the power spectrum. Anytime I show you strain per root Hertz, I've done this. I've given you the amplitude spectral density, okay, or meters per root Hertz. So the reason we do that is that if you think about displacement as an experimentalist, again, you measure things in meters. You don't measure in meters squared. So people like to use the amplitude spectral density. But of course, now you have this other annoying thing, which is what the hell is a square root of Hertz? But that's okay. So it just simply tells us you have to continuously be reminded that when you want to do real units, you have to switch back to the true power spectrum. Okay, so now let's look at an example. So let's think about observing run 1. This is a spectrum amplitude spectrum I've already shown you. And the sensitivity to binary in spirals was about 10 to the minus 22. So that was the RMS, the root mean square amplitude of the gravitational wave. And how can we connect this back to the power spectrum or the amplitude spectral density? Well, it's done quite straightforwardly. This is a statement that the strain, when it had this RMS value of 10 to the minus 22, that means, again, remember for us, that means the measurement period is 10 milliseconds. Why? I've already told you once, because we like 100 Hertz. That's where our measurement band is. And so that simply says that in this measurement band, centered around 100 Hertz, so you go from 50 Hertz to 150 Hertz, if you integrate or add up all, components, frequency components of the power spectrum, that should give you the RMS value squared. So you can now just work backwards from this and come up with that the actual amplitude spectral density should be 10 to the minus 22. I've literally just done this math out. And then, so here I found that we should have 10 to the minus 23 in amplitude of strain. And now how do we connect this back to the displacement spectrum? So to connect back to the displacement spectrum, I have one other thing to do, which is I have to not just divide by the length, which we can do, but I also have to include the fact that I have 4 mirrors. Remember those Fabry-Perot cavities? So now I don't care about the motion of just 2 mirrors. I care about the motion of 4 mirrors. And they are incoherently, they're independent of each other, so they add in quadrature, and I get this extra factor of 2. And with that, I multiply this out, and I should have 2 times 10 to the minus 20 meters per root Hertz in my spectrum at 100 Hertz. Do we? Here's 100 Hertz, and here is 2 times 10 to the minus 20. Okay, so that's a factual statement. So I went through this exercise because I want you to be able to go comfortably from amplitude or power spectra to RMS values. And in the lab, we do that all the time, and I know tonight you're all going to try and build one of these instruments for yourselves, so you should be able to do this. Okay? All right, so now we come to the discussion of limiting noise sources. So let me show you this plot. It's a bit busy, but it's let me assure you this is only a fraction of the whole story. And I'm not going to bore you with the remaining fraction. This is, now you're very used to seeing this. This is just the amplitude spectral density of strain. This is the design for advanced LIGO. The black curve is the sum of all these other curves, and whenever we say this is advanced LIGO's design sensitivity and we show this black curve, here's what's underneath it. The purple curve, the magenta curve, is quantum noise. We're going to discuss that mostly tomorrow, although we already started to discuss it a little bit today. This region right here is the shot noise limit. Okay, this is just the quantization of the photons, the photon counting statistics. The next important noise in advanced LIGO is this red curve, which is called coating Brownian noise. That's a form of thermal noise. There's another kind of thermal noise, which is called suspension thermal noise, which is this blue curve here. It doesn't play as important a role below, above about 20 hertz. So we'll talk about it, but it won't be so important. We'll talk about both these forms of thermal noise. And then another important noise source is this brown curve here, seismic noise. And you notice that the seismic noise doesn't play a role at all in the noise budget for advanced LIGO. That was not the case in initial LIGO. In initial LIGO was limited by seismic noise below something like 50 hertz. Okay, and so seismic noise is now not a problem because of the fabulous vibration isolation systems that we use, and I'm going to show you what those are shortly. And then I'll mention there's a few other things. This yellow curve is a rather interesting one. It says excess gas. This is just how much residual gas you have in your vacuum system. Now, why might you care about that? Well, you might care about that because when you have some column density of gas and your laser beam passes through that column density, that changes the refractive index. So even the few molecules that are left in the vacuum system are important, and you can see the vacuum system is good enough that it's not going to be a problem for advanced LIGO. And I'll speak about this noise source, the green one. The green one is something that we call Newtonian noise. It's written as gravity gradients here. They're roughly equivalent. And this is actually a very tremendously interesting and peculiar noise source. It is a noise source that comes from the fact that you have these mirrors hanging as pendulums, the free-falling test masses of general relativity, and they're hanging downwards because they're hanging towards the local direction of g, the gravitational acceleration. But as you have landmass underneath the test mass change because of passing seismic wave, or above because of a passing cloud, local g changes. And when local g changes, the test mass moves. It's not free falling anymore in that degree of freedom that we care about. And this is the single reason you might argue, there are others, but this might be the most compelling reason to build interferometers in space. Because this is a noise source that you can't do very much about here on the Earth. You can win by factors of 3 to 10 by going underground or by instrumenting around your test mass, measuring all this and trying to cancel it out. But really, if you want to make a detector that's sensitive at 1 hertz, not even 10 hertz, at 1 hertz, this kills you. Okay, so this is the reason to go into space for a low frequency detector.
Is there a specific temperature for those pendulum springs?
Is there a specific temperature? So yes, so the pendulums in LIGO are entirely at room temperature. Everything in LIGO, all the mechanics in LIGO are at room temperature. In the Japanese experiment, Kagra, that's not the case, and I'll say a little bit about that maybe towards the end of tomorrow. Okay, but good. So this is the noise budget. So let's go take a look at these noise sources. Now, here on the left, I've put all the noise sources that. I should introduce radiation pressure noise right here. So this quantum noise is a very interesting noise source. I've told you. We've already introduced you to shot noise, and I've already told you that shot noise you do better by using more laser power. In fact, I spent a bunch of the earlier part of the afternoon showing you how we boost the laser power. Now it comes with a price that I will tell you about. And the price is, as Scott already introduced this, photons don't just carry energy, they also carry momentum. And so what happens now is that as you increase the laser power, and in fact if we go to, where did I go? Limiting noise, maybe it's too far back. As we increase the laser power, we make our shot noise better, but now in this region of the spectrum, so below about 100, between sort of 20 and 100 hertz, this curve here is limited by this momentum kicks of the photons applied to the mirrors. And both of these two together are imposed on this interferometer essentially by the Heisenberg uncertainty principle. This is a fundamental conundrum in quantum measurement, which is that the stronger the measurement you make, the larger the back action. The strong measurement here is we use a lot of photons to probe the phase. The back action is those photons kick the mirror and disturb the phase measurement. Okay? And we'll talk about that in when we talk about the generalized quantum limit. Now these are all the different kinds of noises we will talk about, and on the right are a bunch of noises that are not fundamental, they are more technical but very real, and every experimenter's worst nightmare. But we won't talk about that because when you build your own gravitational wave detectors, these will come a little bit later on, so we'll discuss them at a different summer school. So for tomorrow, tonight you'll build your gravitational wave detectors. You should try to aim for these things, okay? All right, seismic noise. So what's the scale of seismic noise? So the amplitude spectrum of seismic noise above about 10 hertz scales as roughly 10 to the minus 9 meters. So that's basically says it's a nanometer at 10 hertz, and then it's falling off as f squared. So if you wanted to draw this in a spectrum rather than envisioning it in words, you would say the spectrum of seismic noise looks like this. It's something on the order of 10 to the minus 9, and this is in meters per root hertz. And so that's what it is at about 10 hertz. And then above 10 hertz, it's falling off as 1 over f squared. So you can tell if it's falling off as 1 over f squared, then at 100 hertz, it should be 4 orders of magnitude smaller. Okay, so that's 10 to 100 is a factor of 10, 10 squared, so 100. So this would be here at 100 hertz, it would be 10 to the minus 11. Okay, something like that. Okay, so that's what the spectrum of seismic noise looks like. You can tell already that at 100 hertz, this is quite far from the 10 to the minus 18 that we need to reach. So we need roughly 10 orders of magnitude, 9 orders of magnitude of isolation. So how are we going to do that? So the first thing is that mechanical oscillators act as filters. Now, at some point in your physics education, you must have come across a simple harmonic oscillator. Now, the simple harmonic oscillator has an equation of motion that looks like this right here. It's basically just an inertial term, a damping term, and a Hookean or spring constant term. And here's a driving force. Here is a solution to this equation. And when you plug this solution in, you do the algebra, you can make an estimate of the amplitude of in this case, this is simply just the amplitude x, the motion of this oscillator. And notice that it has this Lorentzian form right here. Basically tells you that when the frequency is equal to the resonant frequency, you get this term vanishes and you're dominated just by the damping term. That's this resonance here. So this is another version of the frequency domain that I want to introduce to you. So this is the time domain solution, and this is the frequency domain solution of the exact same thing. And here then is what it looks like in the frequency domain. This is a plot of the displacement over the force. So this is the motion of the bottom of the pendulum, the mirror, to the force applied at the top. And you notice something that's very nice, and this is universal. This is not just for pendulums. This is also true for spring mass systems or any other harmonic oscillator. And what you notice is that above the resonant frequency, notice that the displacement per force is falling off as 1 over f squared. And this then is a filter. It's a filter that says any force that drives this pendulum below its resonant frequency, the pendulum will just move with it. Look at it, it's this unity. So the pendulum just moves with it. At resonance, is amplified, which is not good, and we'll come to that next. But then above resonance, this falls off as 1 over f squared, and very quickly, because of this fall off, it becomes a free particle. And another way to think about this is that above the resonant frequency, only the inertia term dominates in the differential equation. Okay, and that's it. So now you have yourself a filter, and we get this kind of for free, because we were already hanging the mirrors as pendulums to make them the free falling particles of general relativity. And now, so we know that we see that this harmonic oscillator filters as 1 over f squared above its natural frequency. Let me remind you that with 10 to the minus 11 meters per root hertz at 100 hertz, that's certainly not enough. So what we have to do is we have to make a chain of n of these harmonic oscillators such that the actual attenuation factor goes as 1 over f to the 2n. Okay, and n is really, you can put as many as you wish. I will guarantee you experimentally every stage that you add adds an enormous amount of complexity, because these are now coupled oscillators. You work very hard to make them each independent of the other, but they're not. But here is an example I'd already shown. Here is a spring mass system that gives you some attenuation. So here is a single stage here, spring mass, another stage, stage 2, stage 3, stage 4. And when you use this, then you can see a spectrum like this. There's a displacement spectrum again, amplitude spectral density. The blue curve is what the ground is doing, and the magenta curve is what you get in isolation above the natural frequencies of the spring mass system. And you notice this happens at roughly 10 hertz. So above 10 hertz, you get some isolation, some pretty dramatic isolation. Below 10 hertz, you also do some damage, which is the resonances of amplification of motion at the resonant frequency. Okay? Now you can just carry this to the fullest. In Virgo, for example, instead of a 4-level stack like the one spring mass stack I showed you, Virgo has a 7-stage pendulum. So here is the mirror of Virgo hanging from 7 stages of pendulum. And now you can see the very dramatic drop off here. Look at the number of orders of magnitude here. It's actually 2 orders of magnitude per dash line. Blue is the ground motion when you do nothing. The red is the motion after it, at the bottom of the payload, and you can see this dramatic, 15 orders of magnitude suppression. Okay, so that's the trick that you use. Now that's not the only trick that you can use. There's another trick that you can and should use, which is you can also do active vibration isolation. So what I showed you right now is passive. You build a superharmonic oscillator and you use that to do the filtering. Now, active isolation is very similar to the noise-canceling headsets. So people have used noise-canceling headsets, and the principle there is you put your headset on, and then there's a little microphone outside the headset that's measuring the sounds outside. And then it actually applies to the music you're hearing. It applies an equal but opposite sound. So it cancels the sound that it measured outside to the sound that you're hearing inside. And that's called feedback control, and we do similar things here. So I'm going to walk you through a little bit how feedback control works, because this is a tremendous life skill. In experimental circles, and particularly in precision measurement circles, there's I will go so far as to say a law, but maybe it's just a theorem, that says if you can sense it, you can cancel it. Okay? And so just anything that bothers you, you can build a servo around and get rid of, So I'll show you how you do that. So here is a feedback control system, and this feedback control system is sometimes called servo systems, and they're used very interchangeably, so I'll use both words. So there are only 4 elements to a simple feedback control system. The most important element is called the plant. Now it's a very funny word, because this terminology was originally developed in manufacturing. And in manufacturing, what do you want to control? Some manufacturing plant. Okay, so that's where it comes from. In our case, the plant would be the output, say, of the motion of a Fabry-Perot cavity. Another really good example of where we would use this is something that I already alluded to, but I'll draw it again. Remember I showed you if you wanted to operate your Michelson interferometer at mid-fringe, how do you keep it there? The distance between here and here is 200 nanometers. The mirrors are moving by much, much more than 200 nanometers. You do that by measuring this fringe and wrapping a servo system around it. Okay, that's how we do it. So the plant in this case would simply be this measurement of P out right here. Okay, but I'll make it more general than that. That's a plant, and the plant output will be, like in this case, it would be the measurement you make on a photodetector. That's the sensor. Oh, sorry, the measurement would be what the measurement you make on the photodetector would be out here. That's the sensor. You have to have something that can sense. Then you have a filter, and this is something you make yourself. We the engineers design it. And then there's an actuator. An actuator is just a fancy word for a pusher. In the case of pushing on a mirror, it's literally a force you apply on the mirror. In the case of your noise-canceling headset, the actuator is some current source that adds current to the current that's going to the loudspeaker in your headphone. Okay? So that's the actuator. And now let's just go through each of these. The plant is the existing system we want to control or modify. The sensor generates a signal that's proportional to that property of the plant we want to control. The actuator acts on the plant to change its output, and that filter in between this, the compensation filter, is something that is usually a frequency-dependent amplifier, but we get to design that based on all the other parameters. Okay? So let's look at what the signals in the servo loop are. And this is the punchline right here. Here's the same servo. Here I have some input I, and that's the desired input. And look what happened. There's this evil quantity D shows up. D is disturbance. Okay? And now what we want to do is, so now you can see quite easily, I is equal to A, which is the actuator signal plus D. So there's a summing point here, so that's obvious. And then what we do is we simply, now remember I told you another beauty of working in the frequency domain is that you can just multiply rather than convolving. S in this case, I'm sorry to mix units on you, but S in this case is simply just, this is engineering units, but you don't have to worry about it. Just think of S is just imaginary times omega, which is frequency, so it's just imaginary times 2 pi frequency, okay? So just think of it as frequency, all right? And so now the beauty is that as we go around the loop, we can just multiply out, oh, did I lose that? Yeah, we can just multiply out P times S times F times A. And so A over here is simply equal to I multiplied through all these objects, okay? That's it. And we define this PSFA as a quantity G, which is itself a function of S. Each of these is a function of S. So now we just plug back for A in this first equation. I is equal to D plus IG. And now you bring I over, and you notice something rather remarkable, which is that I is equal to D divided by 1 plus G, which we call the gain. That's the loop gain. And so in all of these circuits, we aspire to make G much, much greater than 1. And now notice what happens. If G is much, much greater than 1, my disturbance D is strongly suppressed in I. That's the cancellation. And in fact, if I could make G, enormously large, then I would be identically equal to G. Right? So it approaches G. So that's the thing we try to do. We try to make G very, very large. And now if you look at the plant, if you look at what happens to the thing you actually cared about, which was the displacement. Remember, plant is the interferometer. We care about the interferometer length P. Here's a disturbance coming that's kicking that length. If you look at what P over D is, it's going to be whatever this plant function is, 1 plus G. Again, if you make G very large, you suppress it. Okay? That's how a servo loop works, and we do that. This is a cartoon of how it works for, remember those resonances that I showed you that are amplified? The noise is amplified at the resonance. So here is a case where the blue curve is just the pendulum resonance when there's no feedback turned on, and then the orange curve is when you turn the feedback on and you damp out the resonance. So that suppresses the displacement. Okay? Another example of that is the spring mass system I showed you before, but now you can actively measure the position of the payload and then feed back to something that can move it. And that's in fact how LIGO's payloads are hung. Here is the mirror of the interferometer hanging from 1, 2, 3 pendulums, and then 1, 2, 3, 4 pendulums, and then the top of that pendulum structure, so that's all the passive damping, passive isolation, sits on this very active isolation stack where we measure the motion and cancel it out by pushing on it, okay? And you do all of that, and you got yourself down to the 10 to the minus 18 meters that we, actually it turns out to be much better than 10 to the minus 18 meters. I'll show you tomorrow exactly how good. We're well, the seismic noise is not a problem for advanced LIGO by almost 2 or 3 orders of magnitude. So, done. All right, so let me now just finish up by talking about thermal noise, and then we'll pick up quantum noise tomorrow. So the key ideas of thermal noise is twofold. One is Brownian motion, and the other is the fluctuation-dissipation theorem. And Scott introduced the fluctuation-dissipation theorem to you, and I will do a little bit of that as well. And so we're going to talk about how thermal noise enters the interferometers, and we're going to talk about how we make it, how we reduce it. Okay. So Brownian motion I don't need to introduce very much. Brownian motion, as you know, is basically a random motion that was observed certainly by Brown for pollen on water, but it is the random motion associated, the jitter associated with thermal energy, okay? Now, the fluctuation-dissipation theorem relates fluctuations in a system at thermal equilibrium to the response of that system to an applied perturbation. So it's a fancy words for saying the following. If I have a fluctuating force applied to a system, the amount by which that fluctuating force will disturb the system depends on its dissipation. That's the statement that's being made. Now here is the actual spectrum of displacement power spectrum. It depends on temperature and some frequency stuff, and it depends on this quantity, which is the real part of something called the admittance. Admittance is the inverse of impedance. I like neither of those. I will give you a much simpler version in a moment because it's not very intuitive. But you can, I think impedance is certainly more intuitive than admittance, but it's really just the inverse. Whether you dissipate or not. The real part of F, so this is the important statement. The real part of F is proportional to the dissipation in the system, and therefore determines how much the thermal noise is going to bother you. So looking at this equation, you immediately know you have 2 knobs to turn to reduce thermal noise. The one is to lower the dissipation, so to have lower dissipation in the system through this term, and the other one, of course, is temperature. You can cool or you can lower the dissipation. Those are the 2 knobs you have to turn. So here's a nice little cartoon of the same idea. And I put this cartoon up because, again, I want to remind you that the driving force in this case, the disturbance that drives is Brownian noise. And if you zoom in here, this actually turns out to be a zoom in of the fibers from which the LIGO mirrors are hanging. So there's the pendulum fiber right there. And you notice, and I'll go into more detail there, this point is critical because this is the point that's attached to a heat bath. And so the dissipation, whatever losses there are at this point, are going to affect the thermal noise of motion of the suspension right here. Okay, that's the key thing here. So that's the other thing that's important is, the contact to the heat bath matters. Because if you have a heat bath, but you're connected to it through something very non-dissipative, you won't be thermally excited. So that's the idea. Okay, and then but the version I like of the force spectrum is in terms of this quantity Q of the mechanical oscillator. I just like it better because that's what we measure in the lab. Omega sub m is simply the natural frequency of the mechanical oscillator. Okay, so Q. We like Q. It's a dimensionless measure. It's the ratio of the elastic restoring force to the dissipative force. Q is very closely related to finesse. Remember when I told you finesse was just the rate at which a cavity loses photons? Q is simply the rate at which a mechanical oscillator loses energy. Okay? So, and you can see here's a picture of a mechanical oscillator. It's oscillating away, but it's losing energy. That's the damping coefficient there, and the Q is measured by this ring down right here. Now, Q is related to another very important quantity in thermal noise world, which is the loss angle. The loss angle is a phase lag between force applied to a system and the displacement of the system. Okay, so, and we'll come back to that. So in some round numbers, experimentalist round numbers, a garden variety Q in this field would be something like 1,000. A good Q would be about a million. An even better Q would be about 100 million. And the best Qs that people have seen in mechanical oscillators are in these little nanomechanical oscillators where people are achieving Qs of 10 billion. Okay, so that is a very big deal. Remember, this is a very big deal in many systems, not just in LIGO, because in many systems, particularly in these nanomechanical systems, you're trying not to lose energy, right? So this is a way of not dissipating. Now I'll give you one other connection to Q that's very important. No, I'll tell you that tomorrow. All right, good. All right, so here's a menagerie of thermal noises. So here is a thermal noise spectrum summing over all mechanical modes. So F sub n is simply any mechanical mode of your system. If you have coupled oscillators, you have many of these. If you have a single oscillator, it will be a single one. Phi is that loss angle that I told you about. It scales roughly as 1 over Q. It does scale as 1 over Q. Now, why do I write this in this form? I just want to remind us, again, there's our temperature knob. And the dissipation knob now lives in this phi. And why do we write it like this? Because phi allows us, let me say this first. So we have 3 kinds of thermal noises in gravitational wave detectors that we worry about. One is coming from the mirror substrates itself. So literally the mirror itself acting like a mechanical object with its own normal modes. And so dissipation from that. The suspension thermal noise matters. So this is matters most of all where the fibers can bend, and bending is a place where you can have dissipation because you have a thermal gradient. And then finally, and the one that bothers us the most in advanced LIGO is this optical coating. Remember I told you the glass only reflects 4%? And so to make it reflect highly, we put layers of silica and tantalum, multi-layered coatings. And the stresses between those layers is a dissipation point. Okay, so that's an issue. And phi is important because all of these different thermal noises, you're used to thinking about a spring constant K and a Hookean term, but really the way, and that's very true if you have an completely elastic material, but almost all materials have anelasticity, and when you have anelasticity, the spring constant acquires an imaginary part. And that imaginary part is that loss angle that we're talking about. That depends on Q. So Q is related to phi, and phi is related to the anelasticity of material, so that you can see the connection now, right? So in the end, what's going to happen is if you want to do better with thermal noise and you don't want to turn the temperature knob, the knob you're going to have to turn is better materials. Okay? Yeah.
The first term in the denominator that should be squared, right? Because the units don't have a fraction.
Oh, that could be just because I was lateching it. Thank you, Scott. I will fix it. Yes, that should. Yes, I will check it. I can't even do that in real time, but thank you. Only a theorist would catch that. So, okay. So now where is the dissipation in material? So let me give you some nice rules of thumb. When this loss angle is a function of frequency, we get this viscous damping. Viscous damping is the damping you're all used to. It's the damping that's proportional to velocity. It's the damping that happens when you try to drag a spoon through a pot of honey, of those kinds. When phi is roughly constant as a function of frequency, we get something called structural damping. And this is the damping that occurs in most materials. It is due to internal friction in materials, okay? And the intuitive way to think about this is that it's independent of frequency, because in the bulk behavior of materials, you basically have, so anytime you have relaxation, relaxation means damping, but all the different modes are incoherent with each other and relaxing at different time scales, and so the incoherent superposition of those is just a frequency independent loss. Now, viscous damping has a flat spectrum. So viscous, what does it look like spectrally? Spectrally, in terms of, what am I drawing here? Frequency. And here, let's draw motion per force, where the force is this thermal noise force, okay? For an oscillator that is viscously damped, you get the same thing you saw before. You see that it has some flat spectrum, it has a resonance, and it has a 1/f² fall off. And that's what happens if you took a pendulum and you hang it in a gas. Like if we didn't have a good vacuum system, the pendulum would be damped by this kind of viscous force. Now, our vacuum system is good enough that the other kind of damping we have is this due to the internal structure of the material. And this damping looks like this. It also, at resonance, they're not distinguishable, but then this falls off slightly faster, 1/f². Okay? And that's structural damping. And by measuring in the lab, by measuring these thermal noises, we can tell what mechanism is at play and try to reduce it. Okay? So that's the thing. I'll skip this. I'm running out of time a little bit. So let's just talk a little bit about what determines the Q and thus the thermal noise of a material. So external dissipation, which usually gives us this viscous damping, is things like air friction, rubbing, eddy currents. And this is usually eliminated by engineering. We actually can, you make a good enough vacuum system, you'll do better. If you're having some kind of eddy current damping, you have to just make sure that you shield your materials from metallic surfaces, etc. So that I feel like in experiments is pretty easily done. Internal dissipation depends on the material properties of the materials that we use, and that's much harder to deal with. Okay. All right, so here are some fun things, again, just for you, since I'm hell-bent on turning you into experimentalists. Rubber typically has a Q of about 10. Most ordinary metals like aluminum, tungsten, steel, they have a Q of about 1,000 to 10,000. Fused silica, glass, which is what we use for our mirrors, and you can see why, has Qs of over 100 million. Intrinsically, and then sapphire is another kind of material that also has very high Q. And these are numbers are quoted at room temperature. And why do I quote these at room temperature? Because you'll see that if we ever want to turn the temperature knob to cool things down, we would have to be very careful, because in particularly glassy materials have really lousy Qs as you go cryogenic. So you'll do this wonderful thing of all the work of cooling down, going cryogenic, and you'll win by the square root of the temperature in your sensitivity to strain, but you'll lose much faster because these Qs will go to hell. Okay, so you have to be very careful when you do this balancing. I want to see what's left. Yeah, okay, I have 2 more slides, so I'll skip this. So very good. The very end of the thermal noise story then is the following. We use fused silica wherever we can, because you saw it has this high Q, and especially for the mirrors. And then once we've done that, and we've engineered the suspension thermal noise away, because that can be done by geometry, we're left with the thermal noise that comes from the high reflectivity coatings. And remember, I told you why. Because you have internal dissipation between the layers of materials, okay? So longer term, what we obviously will also have to go to lower temperatures, and the Japanese detector Kagra is already doing that. And then, of course, I think I already said this in as many words, as we go to lower temperature, we can no longer use fused silica. We'll have to go to some crystalline material, because these glassy materials, their Qs go crazy. So this brings me to the end of this lecture and the beginning of what will be the next one. And so, questions?
The temperature distribution of the mirrors, according to that distribution, you use, I think, TM21, right, for the inner cavity mode?
No, we use a TM00.
So why that temperature distribution is like that?
So I didn't show any temperature distribution, but I can tell you the answers. The question is, what is the temperature distribution of the mirrors themselves? So the mirrors are sitting at room temperature, and if you do nothing else, there should be no thermal gradient. It's in equilibrium and it's sitting there. But the moment you shine light onto it, and remember now, because of my power recycling and my Fabry-Perot gains, in Advanced LIGO, when I put in roughly 100 watts of laser power from into the interferometer, circulating in the Fabry-Perot cavity will be nearly a megawatt. It will be 750 kilowatts. Okay, so lots and lots of laser power. Now the mirrors have an absorption, which is again about the best you can do, of about 1 part per million. So you take a megawatt of light and you have a watt of it entering your mirror. It's being absorbed. So your mirror is being heated by that 1 watt of light. Now if your light has a shape, and it turns out that the shape of the light in these optical cavities, and turns out to be the case mostly because you can easily, I shouldn't say easily, if you were interested you could work this out, but the shape of the mode inside the cavity, our cavities are made of spherical surface mirrors, and the shape of the light field inside there is what's called a Gaussian beam. It has a Gaussian distribution of power. So if I now take a cross section across this, the power will look Gaussian. Here, sitting on my mirror, if this is my mirror surface right here. So it has maximum power in the center. Now, so most power is at the center and least power is here. So when the mirror absorbs this and thermally deforms, it's deforming with the opposite shape. So certainly instead of being this spherical mirror that's needed to meet the boundary value problems here, it no longer does that. And so in LIGO, what we do is we actually then come from this side of this mirror. So say from this mirror is now deformed in this way. We come from this side and we shine onto the mirror a CO2 laser. So it's a different kind of laser. It's 10 micron wavelength instead of 1 micron. But this glass is very absorptive for it. So we actually use a laser beam with this profile coming from this side, and we compensate it out. So we actually unchanged the shape that the internal cavity field changed it to. And if you ask, and this will be important for tomorrow's lecture, if you ask, why is Advanced LIGO only use a 100-watt laser? I mean, we know how to make a kilowatt laser now. This is the problem right here. We don't know how to compensate these thermal absorptions. So.
What about continuously freezing?
Continuously
Giving cold temperatures.
Yeah, continuously cooling it. Yes. So look, fundamentally, cryogenics and low vibrations cannot be friends. Okay. And so the amount of engineering that would go into making that relationship is something that we're thinking of for third generation detectors. But really, if you look at any kind of cryo cooling system, the vibrations associated with that would kill us. And so we don't do that.
Did you have a specific preference for the inner cavity depolarization? POS?
Yeah, so yes, so that there is a preferred polarization in the interferometer, but again, for the cavities, this is normal incidence, so they don't care. But
there was a wave plate in the detailed distribution.
That's right, and that's there to compensate for the fact that in one path of the beam splitter, you go through the beam splitter substrate 3 times, and in the other path, you only go through the beam splitter substrate once. And that's so to compensate for the actual path length change, if you will. Yeah. You also can compensate polarization because the beam splitter, of course, is at 45 degrees, so its polarization matters. So you also have polarization compensation. You have both path length, so index compensation and polarization compensation. So in case you didn't follow, when you hit any kind of surface normal to the surface, it doesn't matter what the orientation of the polarization of your light is. But as soon as you have any angle, then the orientation of the angle of your optic and the orientation of your polarization starts to matter. And so the beam splitter matters, the other optics doesn't. Okay? Other questions?
Is there a plan for active cancellation for relatively easily measurable sources of the gravity gradient?
Yeah, so the question is there a plan to use this kind of feedback control to measure the gravity gradient and cancel it out? So there have been many laboratory experiments and tests done of that. It turns out that the amount of instrumentation you need to reconstruct in this case, the seismic wave that went by is pretty large. So the improvements that people have seen in the lab are factors of 2 or 3, and so the plan is certainly for that to be part of something in the next 2 or 3 years, but it's not being used right now. But remember our motto, if you can measure it, you can cancel it. So we put all of our effort into measuring.
I was wondering, what do you use for this kind of active control systems? What kind of instruments do you use?
Yeah, so let me preface the answer to that question by, in LIGO we have over 2,000 control loops. Okay, so which one? Okay, so in the case of the seismic, the vibration isolation system, we might actually use a seismometer. We might use any other kind of vibration sensor, motion sensor, to measure the motion of the payload and then feedback. In the case of the optical system, when you're trying to keep a cavity on resonance, so here's a really remarkable thing. So I'll show you this. So remember I showed you that the optical cavity has a resonance like this? Okay, the width of this resonance is equal to, is scales by whatever the cavity round trip time is divided by the finesse. So typically this cavity can have, if the finesse is several hundred and the round trip time depends on the wavelength, this width can be as much as a wavelength over 1,000 or so. So imagine that, the wavelength is already a nanometer, and so to keep this cavity on resonance over here, you sometimes have to control the position of these mirrors by lambda over 10,000, 100,000, depends on how finely you want to be in the center. So that means you're controlling it to 10 to the minus 12, 13 meters. And that's done by actually measuring the light that comes out of the cavity using a phase-sensitive technique that tells you that the cavity is not on resonance, and then pushing back on the mirrors. So different applications have different sensors. Some are photodetectors, some are seismometers, some are capacitive sensors. You know, there's at least 30 different ones.
As an output, not for measuring.
For the output, yeah. So that's a fine question too. So again, in the case of the mirror, say I'm trying to control the mirror position because I want it to be within this fringe. So the mirror, for example, these mirrors have little magnets attached to them. And then the magnets are sitting inside of voice coils, so just a little coil. And then we can drive current through the coil to make a magnetic force and push on the mirror. So so that's one example, again, of many, many different ones. So.
If no other questions, perhaps it is good time to stop.
Perfect, thank you.